So in this video we're going to take a look at some practice questions on electricity from the second booklet. So first question, we've got people use electric light bulbs for many purposes, from a torch to light up a path home to searchlights, but they differ in the amount of power they use because a brighter, more powerful bulb is going to be using more energy every second. So all bulbs are stamped with two different values, for instance 36 watts, 12 volts. What do these numbers tell you? So they actually tell you two things. So first of all, the first thing it tells you is if you apply a potential difference of 12 volts, it is going to use 36 watts of power. So if you have it connected to a battery, for example, you could work out how long you could use it for. And the second thing it tells you is the 12 volts indicates the maximum potential difference you should apply across it. Anything bigger, you're liable to have too high a current and you're going to damage the equipment. Okay, so you can also use the values to calculate the current and the resistance. So we need to fill in the gaps here, but let's first look at the equations we're going to use. So first thing, the power dissipated by a component is calculated by the potential difference across it and the current flowing through it. So we might be using that one. And we can rearrange that. We'll see we're in these columns, we can use that to calculate the current. So we do power divided by potential difference. The other equation we're going to use here if we want to calculate resistance is the resistance is defined as the potential difference divided by current. There are other ways we could do it using stuff like P equals I squared or P equals V squared over R, but these are the ways I'm going to do it. So to get the current, we would just do power divided by potential difference, which is clearly 3. To get resistance, just do potential difference divided by current. Again, current, power divided by potential difference divided by current, and then both of those two steps together would get you the final one. So these are the two equations I would use here. Okay, so we're going to look at some like resistor combining and using it to calculate battery current. So all of the different combination laws that you know, the series combination law and the parallel combination law, the purpose of those is to figure out the current being delivered by the battery. That's what we use them for. So first of all, in this circuit here, what we need to look for is two resistors we can describe the relationship between. So the 4 and 6 in this circuit are clearly in parallel with each other. The potential difference across them is the same. But the 4 and the 5 we would not describe as being in series because they don't have the same current going through them. So that's how I think about it. So what I'm going to do is we're actually going to combine together the two parallel resistors using the reciprocal rule, and that gives us a value for the resistance of the 4 and the 6 combined. So what we can do now is we can redraw the circuit like this. We've essentially replaced the two resistors with one resistor, but the battery current will be the same in this scenario. And then once we've got this, calculating the current is pretty straightforward. We're going to do potential difference divided by the resistance, and that gives us a value for the current. Okay, so let's go on and have a look at a different one. So here, the first thing I'm seeing is you've actually got two series resistors. The 4 and the 4 are in series, so we can just add those together. And then the 8 ohm resistor formed and the 12 will be in parallel. So what I'm going to do is actually put those two steps together and use the reciprocal rule, but with the 4 plus 4 in there. So then we can calculate the total resistance, and now our circuit looks like this. We've taken all three resistors and replaced them with one, and now it's really straightforward to figure out what the battery current is using the definition of resistance, essentially. Okay, so this is getting a little bit more complicated, but actually not much. What we've got here are two parallel sections. So what I'm going to do is calculate the resistance of each of those parallel sections of the circuit using the reciprocal rule. And now what the circuit looks like is this, because those two sections are in series with one another. And once we've got that, it's fairly straightforward to work out what the battery current is, in this case 2 amps. Okay, so we've got a circuit, we want to calculate the current through the 6 ohm resistor. Okay, So I'm going to use R equals V over I. So the key thing is the current through the 6 and the 3 is going to be the same, and it's going to be determined by the total resistance in that section. So we know the potential difference across the 6 and the 3 ohm resistor total is 4, and we know the total resistance is 9. So then we can work out what the current is passing through both of them. And then for the potential difference across the 12 ohm resistor, I'm going to use the potential divider rule here. So the potential difference across both of them is 4, and then we're going to multiply that by the ratio of the 12 and the total resistance, and that gives us 3.2 volts. We could have done this question by working out the current passing through the 2 by doing 4 divided by 15 and then timesing that by 12, but that comes out as the same thing. So now think about 3 resistors in parallel. So what we're going to do here is work out the conductance of each resistor. So conductance is just the reciprocal of resistance. So resistance tells you for a given potential difference what the current is going to be, and conductance is kind of the same, so they're very similar concepts, but conductance is 1 over R. So once we've got that, we can essentially do 1 over all the resistance, and that gives us our conductance in Siemens. So that's the capital S stands for the unit Siemens, which is the unit of conductors. It's not seconds. So which resistor will carry the largest current? So all of these 3 resistors here have the same potential difference across them, so that's not going to be a factor here. So if they have the same potential difference, the one with the smallest resistance is going to have the biggest current. Or another way of phrasing that is the one with the biggest conductance is going to have the biggest current. Those two are the same thing. So the 2 ohm is going to have the biggest current here. So what is the combined conductance of the resistors? So with resistors in parallel, we just add their conductances together, because remember this is the same as adding the reciprocal of the resistances together. We've basically done the same thing. So that gives us 0.8 Siemens. So the battery is made up of 2 1.5 volt cells of negligible internal resistance. Calculate the current through the cell. Okay, so the equation we're used to is R equals V over I, which we can write as I equals V over R. 1 over R is equal to conductance, so we can rewrite this as I equals VG. And then we know the value of potential difference, because it's 2 times 1.5. We know that the conductance is 0.8, and that gives us our value. Okay, so moving on to look at resistivity and conductivity. Conductivity, if you haven't met it, is just 1 over the resistivity, so it's pretty easy to calculate. Okay, so the resistivity is 1.6 times 10 to the minus 8. What is conductivity? Well, it's just 1 over that number. And so we have to be a bit careful with the symbols here. So we've got a sigma for conductivity and a rho for resistivity. And then the unit for conductivity, we could write it as ohms to the minus 1, meters to the minus 1, but remember ohms to the minus 1 is a Siemens, so we usually write it as Siemens per meter, but it's not wrong to write it as 1 over ohm meters either. So if you have a 3 meter length of wire with resistance 10 ohms, what is the resistance of 6 meters of this wire? So we've doubled the length, and resistance and length are directly proportional as long as area and temperature are the same. We've been given no indication that they're different, so I'm going to assume they're the same. So therefore double the length gives you double the resistance. And what length of wire has a resistance of 100? Well, we know that 3 meters has a resistance of 10, so it's hopefully fairly straightforward to see that 30 meters is going to give you 100. But this is actually the calculation I would do to show what I'm doing. 2 lengths of copper wire lie on a bench. Each is 2 meters long, but A is thicker than B. Which wire has the greatest conductance and why? So conductance is directly proportional to cross-sectional area, and area is calculated by doing pi d squared over 4. So area and diameter squared are directly proportional too. So putting those two things together, conductance is directly proportional to diameter squared as long as temperature is the same. So the thicker you are, the bigger conductance you're going to have, or the larger current is able to flow through, essentially. What can you say about the conductivities of the two wires and why? They're both made from copper, the same material, so they'll have the same conductivity, just like they would have the same resistivity, if that were the question. The resistance of wire A is 10 ohms. Its cross-sectional area is twice that of B. What can you say about the resistance of wire B? Well, resistance is directly proportional to 1 over A, or inversely proportional to A if you like. They're the same thing. So resistance of B is going to be 20. If you halve the area, you're going to double the resistance. Or we could say you've halved the conductivity. That's the same thing. So the rod shown in the diagram is made of mild steel. The resistivity of the steel is 1.8 times 10 to the minus 7. Calculate the resistance. So first thing I'm going to do is calculate the area. So I'm halving the 5 millimeters to get the radius because we're doing pi r squared. We're modeling the cross-sectional area as a circle, remembering to convert into meters. So usually with these calculations we end up with a very small area, and then we just pop it into the equation. We know the resistivity, we know the length, we now know the cross-sectional area, so we've got our resistance in ohms. So what length of an alloy, resistivity 5 times 10 to the minus 7, diameter 0.5 millimeters, is required to make a 6 ohm resistor? All the resistors in the lab that we use are just basically wires, sometimes coiled up to make them smaller, but they are just wires. So again, we're going to halve the diameter, square it, and times by pi to get our area in meters squared. We're going to rearrange the resistivity to make the length the subject, and then we can put the numbers in to get our length. So the heating element of a hairdryer is made from coiled nichrome wire. The diameter of the wire is 0.46 millimeters and the length is 7.3 meters. Calculate the conductance of the element at 0 degrees Celsius. The conductivity is 9.1 times 10 to the 5 Siemens per meter. Okay, so again, first stage, I'm going to figure out what the area is by doing pi r squared, remembering to convert into meters. And this is our equation for conductance. So conductance is conductivity times area over L. So it's basically the resistivity equation flipped upside down. So once we've got that, we can plug our numbers in and we get our conductance in Siemens. So copper track on a printed circuit board is made from copper foil 35 micrometers thick. The width of the track is 0.16 centimeters. The resistivity is 1.69 times 10 to the minus 8 ohm meters. What is the resistance of a 1 centimeter track? So again, calculating the cross-sectional area. This time it's not a circle, we're modeling it as a rectangle. So we're doing thickness times width. Again, converting into the appropriate units. And then we're using the equation for resistance using resistivity, plug our numbers in, and gives us our resistance. Okay, so now we're going to introduce some uncertainty into our calculation for resistivity, just like we would in the kind of practical sense. Okay, so we're trying to measure the resistivity of a doped semiconductor chip, and we've got the following measurements. Okay, so calculate the resistivity of the semiconducting material and give an uncertainty with your estimate. So, how are we going to do this? First of all, we're going to get the cross-section area by doing the width times the thickness, just like we did in the last question. And we're going to calculate resistivity using this equation, which we're going to need to rearrange. The other thing we're going to do is I'm going to substitute in V over I instead of R, and I'm going to put width times thickness in for the area. But otherwise, it's the same equation. So you can see we've got 5 measurements contributing to the uncertainty in resistivity. So because they're all multiplied and divided, we're going to need to calculate the percentage uncertainty in each of those 5 factors. And we're also going to need to add together the percentage uncertainties in each of those factors. And then once we've done that, we can then calculate the percentage uncertainty in the resistivity, which we can then convert back into uncertainty using the expression. So those are the kind of the 3 stages I'm going to go through. I stuck these into a spreadsheet to do the calculations for me. So I calculated the percentage uncertainties of each of those 5 factors, added them all up, calculated what the resistivity is using that equation, remembering to convert milliamps and millimeters and so forth, and then from that got an uncertainty of 0.0006 in the resistivity, so in ohm meters. And then next question, very similar. So again, you can see I've ended up the table. So just explain how we got the data. Here's how we calculate the cross-sectional area. Here's how we get the conductance and therefore the conductivity. Again, in place of conductance, I've replaced that with I over V. In place of area, I put pi d squared over 4. And we've done exactly the same kind of stages, but we need to remember to multiply the percentage uncertainty in the diameter by 2 because it's squared in the equation, and that gives us the values you can see on the right-hand side. Okay. So satisfy yourself by a simple arithmetic check that an uncertainty of 4% plus or minus in a resistivity gives about the same percentage uncertainty in the conductivity. So let's make this as simple as possible. This is our link between conductivity and resistivity. So let's let the resistivity equal 1 ohm meter, and therefore the conductivity is also going to be 1 Siemens per meter. Hopefully that's fairly obvious. And then the maximum resistivity is when we increase it by 4%, so times it by 1.04. So that gives us 1.04 ohm meters. So if we do 1 over that, that should give us the minimum conductivity, because remember they're inversely proportional to each other. So if we do 1 over that, you can see we get 0.96 Siemens per meter. If we take 4% off of the 1 Siemens per meter we had earlier, we also get 0.96. So to two significant figures anyway, we get exactly the same value. So that's why we conclude a 4% percentage uncertainty in resistivity gives you 4% percentage uncertainty in conductivity. And the kind of logic going on there is the 1 doesn't actually contribute any uncertainty. It's an integer, so it has 0 uncertainty. So we would expect the same percentage uncertainty. Alrighty, so let's do some extra practice using Kirchhoff's laws. They're some of the most important laws you ever learn in circuitry, so it's important that we master these. So ammeter A5, which is if you can't read it, it's the one at the bottom with the 2 resistors, reads 3 amps. All the resistors have the same value of 10 ohms. What are the readings on all the ammeters, and therefore what's the terminal voltage on the battery? Okay, so the terminal voltage on the battery is pretty straightforward to figure out. We've got 2 10 ohm resistors, each with a current of 3 amps. So if we do 20 times 3, that gives us a terminal voltage of 60. So that's fairly straightforward. So in terms of figuring out what's the different R's, so A2 is the easiest one to figure out next. A5 is the current through 2 resistors. So A2 has half the resistance, so it's going to be double the current. So it's 2 times 3 gives you 6. A3 and A4 are going to be the same, and they're going to be 1/3 of A2 because they've got 3 times the resistance. So that's going to be 2 amps. And then the next ones, we're just going to be using Kirchhoff's current law. So A6 is A4 plus A5. So that's 3 plus 2 gives you 5. And then A7, A8 and A1 are all just going to be A6 plus A2 gives you 11 amps. Okay. So a voltmeter across R reads 24 volts. What is the voltage across the upper 10 ohm resistor? So we can apply Kirchhoff's voltage law, or his second law. So the sum of the EMFs is 40. The sum of the PD across R is 24. So the PD across 10 must be essentially the difference between those. So it must be 16 volts. So that it returns to the battery with no net change in energy. So what is the current through it? Well, we can use R equals V over I rearranged to figure out the current, because we know the potential difference, we know the resistance, so therefore we know the current. What is the voltage across the lower part of the parallel circuit? Well, we can essentially apply Kirchhoff's second law again, so it must also be 16, because it must have the same energy change as across the 10 ohm, is the way I think about it. So what's the reading on the ammeter? Again, potential difference divided by the resistance, so it's going to be 0.4. Or we could also think it's got 4 times the resistance, so it must have a quarter of the current. Either way gets you 0.4. So A1 and A3 will be the sum of those two currents, so it's just going to be 2 amps, because those two have combined together by the time they go through A1 and A3. So what is the value of R? Well, we now know what the current is going through R. We know the potential difference across R, so we can figure out that it's 12 ohms overall. Okay, so then some more complicated Kirchhoff's laws practice. So use Kirchhoff's first law, i.e. his current law, to find an expression linking the 3 currents. So if we look at the junction at the top, I1 and I2 are going in, I3 is coming out, so I3 has got to be equal to I2 plus I1, or I1 plus I2, they mean the same thing. Use Kirchhoff's second law, i.e. the voltage law, to find an expression for the left-hand loop, and then use V equals IR to replace any voltage with current and resistance. So if the sum of the EMFs in the left-hand loop is 12, the currents are both going in the same direction, so those are both going to be positive numbers. So we can see it's going to be whatever the potential difference is across the 4 ohm plus the potential difference across the 3 ohm resistor. And then what we can do is we can replace V4 with 4 times I3, and then we can do replace the V3 with 3 times I1. So if you're asking yourself, how do we know those are I1 and I2? Well, if you think about it, I3 has got I1 and I2 combined. And then at the end of the I3, I2 goes one way, so therefore I1 must go the opposite direction. And the other thing is, you can see the 3 ohm resistor is in series with where we've written I1, so you could know it from that as well. And then once we've got that expression, we can repeat this. It says for the left-hand loop, but I assume it meant to say for the right-hand loop. So the sum of the EMFs in the right-hand loop is 5. We've got V4 and V2. And then we can replace both of those with I times R again. And then we've now got 3 expressions. So it says 3 simultaneous equations. We've got these 3 expressions we've generated so far. So what I'm going to do first of all is I'm going to substitute, instead of I3, I'm going to put I2 plus I1. So that's the first substitution I've made. And then what we've got here is one equation we've got 6I2 and the other equation we've got 4I2. So I'm actually going to multiply the top expression by 2 so that we have 12I2. Multiply the bottom expression by 3. So again we have 12I2. And then I'm going to subtract the 10 from the 36 to get 26, and I'm going to subtract 8I1 from 21I1, giving you 13I1, and therefore we can see I1 is 2. We can now stick that back into the equation and solve what I2 is. So actually we got I2 in the wrong direction when we started, but that's not really an issue. And then using this expression, we can then calculate what I3 is. So that's how we can approach this using Kirchhoff's laws. Okay, let's have a look at a final pretty horrific Kirchhoff's law question, but we're going to use exactly the same principles. So apply Kirchhoff's second law to the bottom right-hand loop to determine the voltage across the 2 ohm resistor and hence the current through it. So since we're looking at the diagram on this slide, I'm going to show you all of the loops so we can identify which EMFs and potential differences are going to be positive and which ones are going to be negative. So let's stick some currents on. So I'm going to be using I1, I2, I3 in the notation. So these are the directions I've decided they're in. They may well be wrong, but those are the ones I've decided. So the number basically tells you the size of the resistor it's going through. So in my logic, we can see I2 and I3 are combining to give you 3 amps. So let's have a look at the different loops. So a loop I'm going to use a little bit later on is this one. We can see that the EMF source is in the same direction as my loop, so it's going to be a positive EMF source. And both of the currents in the resistors are in the same direction as my loop, so they're both going to be positive potential differences. That loop's nice and easy. Again, with this loop, the EMF is in the same direction as the loop, so it's going to be positive, and both of those two currents are in the same direction as my loop, so those are going to be positive potential differences. A little bit later on, I'm going to use this big loop around here. So we can see that V is in the same direction as the loop, so that's positive. The potential difference across the resistor 1 is again in the same direction, so it's going to be positive. The 20 volt EMF source, however, is in the opposite direction to the loop, so that's actually going to be minus 20 volts of EMF in terms of that loop anyway. The final loop I might end up using is this one. So we can see the sum of the EMFs in this loop is 0, because there aren't any EMF sources. I1 and I2 are in the same direction as the loop, so those are going to be positive. I3 is in the opposite direction, so the potential difference across the 3 ohm is actually going to be a negative or minus number. Okay. So that's kind of our starting point. So it wants us to apply it to the bottom right-hand loop. So if we apply that, we can see that V2 has got to be 20 minus 12. Where's the 12 come from? Well, it's 3 amps times by 4. That's the potential difference across resistor 4. Sum of the EMF is 20. Subtract 12 across the 4 ohm. That must mean we've got 8 volts across the 2 ohm. Let's now calculate its current. So V2 we know is equal to I2 times R. So therefore we can see I2 is going to be 4 amps there. Either way we solve it, we end up with those values. Okay. Alrighty, so determine the current through the 3 ohm resistor using Kirchhoff's first law and hence the voltage across it. So we said that I2 and I3 are combining together to form I4. So if we want the I3, we're going to do I4 minus I2. I4 is 3 amps, I2 is 4 amps, so actually I3 is minus 1, which essentially tells us we got I3 in the wrong direction when we initially guessed its direction. And if we know the current, if we multiply that by the resistance, that's going to give us what the potential difference is. So it's minus because we got it the wrong way round. Okay, so this next question is when the direction of the currents becomes important. So using Kirchhoff's second law to the upper loop, the loop with no EMF sources in it, determine the voltage across the 1 ohm resistor and hence the current through it. Okay, so the sum of the EMFs in that loop is 0 because there aren't any EMFs in that loop. So the current going through the 3 ohm resistor is going in the opposite direction to the loop direction. So that's why there's a minus sign in front of it. But the potential difference is also negative, which is why it's minus minus. So when we put those two together, we can see that V1 is equal to minus 11 volts, which means we got the current through it in the wrong direction when we guessed earlier. But the size of it we can see is 11 volts. And having got that, we can see that the current is going to be minus 11 amps. Because if we've got the PG the wrong direction, we must have got the current in the wrong direction. To apply Kirchhoff's second law to the entire outer loop, determine V. So the sum of the EMFs is going to be V minus 20, because they're pointing in opposite directions, but V is in the same direction as the loop. The potential difference we've just calculated is minus 11 in that loop, and that's the only one. So we can see that V must be 9 volts. Okay. So check your answer by applying Kirchhoff's second law to the bottom left loop. Be careful with the direction of voltage here. So in that loop, the sum of the EMFs is V, and then the sum of the potential differences is minus 3 plus 12, and that we can see gives us a total volt EMF in that loop of 9 volts. So we got the same thing, and that finishes off this video.